Intro Chemistry Flame Tests Experiment. If an atom or molecule is heated to a very high temperature, the various electrons contained within are excited to higher energy states. And then as electrons undergo relaxation, meaning falling back to lower energy states, photons of that energy difference are given off. Now, since the human eye can see in the visible region of the electromagnetic spectrum, any photons given off in this region will be seen as one characteristic color corresponding to all the visible photons combined, if there are more than one emitting at the same time. In other words, if you have multiple colors emitted, your eye cannot distinguish. The eye would see a mixture of the various colors. Also keep in mind that other transitions, such as emissions in the infrared or UV, may also be emitted, but our eyes cannot see them. Now, 9 types of EMR, electromagnetic radiation, are shown with their approximate divisions in nanometers in the table below. Note that the visible region lies between 400 and 800 nanometers approximately. So we start at the far end, the highest energy, shortest wavelength radiation are gamma rays. These are high frequency, short wavelength, but high energy. And then somewhat lower in energy are X-rays, then ultraviolet, and then between ultraviolet and infrared is the visible region of the spectrum. Moving to lower frequency and lower energy but longer wavelength, we have infrared, radar, FM, TV, shortwave, and AM. And these have the longest wavelengths, but the lowest energy and the lowest frequency. Note that the visible spectrum is approximately between 400 and about 800 nanometers. In Figure 2, we see the emission spectrum for a sodium atom. So here, if a sodium atom is heated, an electron can be promoted, for example, to a 5p orbital. When it relaxes or falls back to the 3s orbital, it emits a photon with this amount of energy, 4.35 electron volts, which has a wavelength of 285 nanometers, which is outside the visible region. It's in the UV. An electron falling from the 4p orbital to the 3s orbital emits photons of wavelength 330 nanometers, also in the UV region and not visible to the human eye. But an electron falling or relaxing from a 3p orbital to a 3s orbital emits a photon of wavelength 590 nanometers, and this is in fact in the visible region. Let's take a look. So it would be approximately this orange-yellow color, approximately just below 600. On the next page, we see a more complicated diagram for emission spectroscopy, again of sodium. Notice that some of the energy states are split a little, owing to slight differences within the atom, but we need not concern ourselves with these differences. Notice the general orbital energy levels: 3s, 3p, 4s, 4p, 5s, 5p, 6p, and so on. So there are many possible energy transitions within even a simple atom. You'll notice that the wavelength of photon emission and absorption between the 3s and 3p orbitals is given in units of angstroms. 10 angstroms makes a nanometer. So this value of approximately 5,900 angstroms translates to 590 nanometers, which is a yellow-orange light that falls within the range of the visible spectrum. So what's actually happening during this process of absorption and emission? Well, we use metal salts like sodium chloride, Na+Cl-, and we place them in a flame. Now in the flame, the ions, the metal cations, are actually reduced to the elements, so we actually would form, for example, sodium metal. This happens because the fuel of the flame, methane or ethane, are actually reducing agents, something you'll learn more about in organic chemistry later. So the metals then absorb energy in the form of heat, causes their electrons to jump to vacant higher energy orbitals. Then the electrons relax, and this occurs quite rapidly. Approximately 10 to the minus 15 seconds is the time before relaxation. Electrons fall back to lower energy orbitals, emitting a photon of radiation whose energy and wavelength corresponds to the energy difference between the orbitals. Now note that electrons can climb orbital stairs, if you will, in discrete integral quantities. So what I mean here is when you climb the stairs, you can climb them one at a time, or two at a time, or perhaps on a good day 3 at a time, but you can't climb the stairs 1.5 steps at a time, or 2.5 steps at a time, because there's no place to put your foot. Well, similarly, the elements have different distances between their steps. Each element has different energy gaps between orbitals, so each element emits its own unique spectra. It's like a fingerprint. So every element can be uniquely identified and even quantified using emission spectroscopy. Some metals have energy gaps between orbitals that correspond to the energy and wavelength of visible light, between 400 and approximately 750 nanometers, allowing these transitions to be visible to the human eye. So in this experiment, you will investigate a number of different atoms and the colors of photons that they emit upon heating, and so they're called flame tests. On page 3 is a procedure, but I'll explain this as I demonstrate. And then we see a list of the salts that will be tested. For each of these, you're asked to write the chemical formula and record the flame color to the best of your ability to describe it. And then, using that flame color, compare it to the chart of the visible spectrum and do your best to estimate the wavelength that's being emitted. So it's an analog scale, and the rule of thumb is that you read analog scales to 1/10 the smallest division. Let me illustrate. So go back to page 1. Right, so the smallest division is 100 nanometers. It's an analog scale, not digital. We interpolate or estimate to 1/10 the smallest division. 1/10 of 100 is 10 nanometers. And so, for example, if you had a color that you thought was about here, then you could say, well, that's 530 nanometers. You could say it's 540, your best estimate, but you couldn't say 535. You can only estimate to 1/10 the smallest division. That's the nearest 10 nanometers. Now, for those of you who are doing this experiment remotely, online, I apologize because the color rendition of the camera in these videos is probably not nearly as accurate as your eye, but nonetheless, give it your best estimate. Well, let's take a look at these flame tests, and then we'll come back and discuss what else you need to do for the purpose of the lab report. So the first test is sodium chloride. It's a colorless, or you might say white crystalline salt, but in the flame it has this distinctive color. Now, the proper way to do a flame test is to use a platinum wire. And the platinum wire will not melt, and nor will it add any color to the flame. And that would be best, but of course it's expensive, and then you'd have to clean it thoroughly between each test to prevent cross-contamination. A cheaper and easier way to do this is to do what I'm doing here, is to use wooden splints. Disposable wooden splints. So we soak them in distilled water, use a fresh clean splint for each test to avoid contamination. The downside is that if you're not careful, sometimes the wooden splint will start to burn, and that gives this characteristic color of burning wood, which can interfere with the color you're trying to observe from the metal. But so you'll do your best to try and remove that from your decision, and then estimate the wavelength by comparing the flame color to what you see on the chart behind. Let's try the next one. So next we have sodium nitrate, also a white crystalline salt, looks about the same as sodium chloride. What about the flame color? The flame flame color looks about the same as sodium chloride, doesn't it? So the point in testing both sodium chloride and sodium nitrate was to emphasize the fact that what we're seeing is the absorption and emission of sodium. It has nothing to do with chloride or nitrate. Now both chloride and nitrate will absorb and emit, but they do so in the UV, and the human eye would not be able to pick that up. What we're seeing in both cases is simply the metal absorption and emission spectra. This is barium nitrate, another white salt. You can see a light yellow color, white yellow. But there's also a pale green there. And for the purpose of this exercise, please report the wavelength that you think corresponds to that pale green color. Alright, next we have calcium nitrate. It's a colorless salt. Some of it's dripping into the burner. I'll have to clean that out before the next test. Ignoring the yellow from the burning wooden splint, what wavelength would you assign to the color of calcium? Next we have strontium nitrate, another white crystalline salt. Ignoring the yellow color that might be from the burning splint, what wavelength would you assign to the emission of strontium? So next we have lithium nitrate, yet again another white crystalline solid. Seems to require a little hotter temperature to get this to emit. I'm trying to avoid dripping liquid on the burner. There it goes. Alright, so ignoring any yellow that you see possibly from the burning splint, what color, what wavelength would you assign for the emission of lithium? Next we have potassium nitrate, and you guessed it, it's a white crystalline solid. Potassium actually emits two wavelengths in the visible spectrum. So aside from that yellow-orange color, can you see the pale lavender color? What wavelength would you assign to that pale lavender color emitted by potassium? Next we have copper 2 nitrate. And this is not a white crystalline salt. It's wet, but it's definitely got a blue-green color. And the flame color is also kind of a blue-green color. Trying to avoid dripping the liquid onto the burner. What wavelength would you assign to the emission of copper in copper 2 nitrate? So now we have copper again, but this time in copper 2 chloride instead of copper 2 nitrate. The salt looks a little bluer to my eye. And the flame has some green, but I think it has a bit of blue as well. So the nitrate must have some effect on the energy gap between the copper orbitals. What wavelength would you assign to the emission color for copper in copper 2 chloride? Next we have magnesium chloride, a colorless crystalline solid. It's in the flame. There's no color at all. What do you make of that? No, there really isn't any color from the magnesium. How can you explain that? Last but not least, we have iron 3 chloride, ferric chloride, rusty looking. Notice not only the flame color, but the fact that iron characteristically throws sparks as it burns. What wavelength would you assign to the emission of iron in ferric chloride? Alright, so we need to go back and look at the lab procedure and explain more about what's required in the lab report for this experiment. For the lab report, you will write a formal but brief lab report and include the completed table shown above here in your lab report, and propose 2 reasons why no color is seen with magnesium chloride. There's also a short nomenclature assignment associated with this experiment, and that'll be explained in class. And for those of you who may be viewing this online, there'll be a separate video for that. Thanks for watching.